Welcome, Sedef.
Hello. Hi, everyone.
And we are going to talk about privacy-enhancing technologies and not to lose time because it's a very crowded event. So I will give you the traffic stage.
Thank you. So can you guys see my screen with the full presentation?
Yes.
Amazing. Thank you so much. Hi, everyone. So welcome to the Vector stage at this time. So it was amazing to hear from Devil. So we work together at Vector. So we're doing some, sustainability and climate change and AI space. So hope you enjoy his talk. And today I would like to talk about one of our project called Privacy Enhancing Technologies. And so I will share some of my our insights and observations from the project. So it's great to be here today. So before I start, I would like to thank the Turkish AI team for inviting me to this event. I hope you all enjoying the event and talks. And I hope that in the future, we can see each other in person. So here's my agenda. I'm going to start by introducing a Vector Institute a little bit for those who are not familiar with the Institute, who we are, what we do. Then I will give a very short introduction to privacy enhancing technologies, why they are important, and talk about our recent project involving pets and sample use cases from the project. And finally, I'll be sharing some lessons learned and key observations from the project. So my name is Sedef Akınlı Koçak. I'm the Director of Professional Development here at Vector. My team and I develop applied AI programs for Vector sponsors and partners. Prior to this role, I was a senior manager at Vector, where I engage our sponsors on applied AI projects. And I led several large-scale multi-industrial projects, such as involving natural language processing, computer vision, and privacy-enhancing technologies. And I am holding a PhD from Toronto Metropolitan University, also known as Ryerson, where I was focusing on modeling software-intensive system for sustainability. So before I dive into pets, I would like to talk about Vector Institute for those who are not familiar with the Institute. Vector is a non-for-profit research institute founded in 2017. As a part of the Pan-Canadian AI strategy. And our mission was driving AI research in Canada with the explicit purpose of fostering economic growth and having a positive impact on the life of Canadians in general. So to achieve this mission, Vector was created as a research institute, which means our researchers are focusing on world-class research on machine learning, especially deep learning. And we publish in leading academic conferences and journals around the world. And we also want that research to translate into the real world and be impactful, right? So for this purpose, we work with the industry, we work with the government and the other institutions to facilitate adoption of AI. So we have over 700 researchers now, and we started with something like 10 or 12 at the beginning in 2017. And a part of this is to create this healthy ecosystem in Canada. And we need to ensure that there's a large pool of talent. And we also work with universities to foster AI master students through scholarship, internship opportunities, and so on. So the other thing that I wanted to mention is here who our partners are. So in terms of the government partners, we work with both federal and provincial government. And representatives of both levels of governments have joined our project, for example. And we also collaborate with our sister institutions, AIM in Edmonton and MILA in Montreal. In terms of the companies that we work with, basically, to facilitate, we have engaging a long-term commitment with about like a corporate partners that collaborate in our program to facilitate the knowledge transfer. We have about 30 enterprise sponsored companies, and some of them you can see here in this slide. And we also have community of more than 25 startups and scale-ups to bring the talent and technology expertise. And these are AI first or AI-centric companies. So the last thing that I wanted to mention about Vector is the way we work in the companies. So basically, we have divided into 3 areas. First one is a technology, the second one is a teams, and the last one is training in terms of the technology. So what we do mostly is we support participants in the development of their technical capabilities through demonstrations, open source codes, and hands-on experimentation with the state of the art in AI. So basically, we highlight opportunities for these companies, as well as providing one-to-one access to some of the best AI talent in the world, and to guide them they're like generating insights from those experiences. So in terms of training, we provide like different training opportunities to ensure that the company's participants are kept current with the latest development in this very fast changing world, so to speak. So before we dive into our project, let me review privacy enhancing technologies in very high level. So bear with me. As you all know, to train a machine learning models, all the data needs to be moved to a single machine or a cluster of machines in the data center. So this can be difficult for most of the industries where data is competitively sensitive, restricted by the regulations, or subject to privacy considerations. In recent years, there have been significant development that we have transformed the privacy enhancing technologies with the potential to transform the fundamental nature of the data sharing. And these technologies make it easier and safer at somewhat to apply machine learning in the most regulated, competitive, and let's say profitable industries. And accessibility and availability of very high quality data is somewhat pivotal to leverage the power of AI, and as it makes more algorithms like more accurate, reliable, and useful. However, some of the a major concern of the machine learning system is maintaining the privacy of the data that was used to train, right? So some of the organizations have considered anonymization as a method to address this risk, but some studies show that this process is not enough. So data can often be reverse engineered to re-identify individuals. So for instance, you probably heard a while back, an anonymized Netflix dataset of film ratings was de-anonymized by comparing the ratings with public scores on the IMDb with film video website. So there are numerous privacy attacks perpetrated by someone we call adversary. This adversary is a party looking to reveal the information about the data that a model is trained on. So one type of attack is the membership inference attack, shown on your right side, where the adversary tries to confirm whether a specific sample was used to train a model. So even if the adversary doesn't have an access to the data explicitly, access to the model or its output can reveal the information about the data that the model was trained on. So this is where pets come into place. So pets are technologies that embody fundamental data protection principles by minimizing personal data use and maximizing data security. And these technologies could address relevant use cases such as private collaborative learning and re-identification risk reduction. Some of the methods include federated learning, both horizontal and vertical, privacy-preserving record linkage, differential privacy, homomorphic encryption, and framework called confidential and private collaborative learning, or CAPC. Here is the list of example use cases where these technologies can be useful. For example, the application testing and data analysis are sometimes handled by third-party providers. And even when they are handled in-house, the companies should minimize the internal access to customer data. So another example would be like a financial institutions. Those institutions are highly regulated, and they are responsible for protecting the privacy of the customer data. Another area is healthcare. Again, it's like patient privacy is very important in this case and highly regulated area. So pets can be crucial to helping those kind of areas for organizations. And just a brief introduction to federated learning. As mentioned earlier, there are two types of federated learning. One is horizontal federated learning and vertical federated learning. And horizontal federated learning is employed in the case that where we have two organizations that have the same set of features and labels, and they are looking to collaborate to increase the user's sample size of the data set, right? So, but they can't explicitly exchange the data across organizations. So they're going to actually jointly train a model where only the local gradient updates are shared. So you are not explicitly sharing the data across the organization. So there's also a vertical federated learning, which happens in the case where there are, again, two or more organizations that have an intersection of users in this case. So, but they have different features about the users. So they are looking to collaborate or train a machine learning model that leverages the feature set from both of the organizations. In case of the vertical federated learning, one of the subtleties is that we have to match the records that refer to the same entity across sensitive data sets. And this is a non-trivial task in practice. So this is what we call privacy-preserving record linkage. In general, for horizontal federated learning, the algorithm to train the joint model is more straightforward. So let's say there are a few hospitals that agreed on a specific model structure. Then they start by initializing each of these models within the same set of parameters. So they're going to train on the local data and upload the gradient updates to the global model, which aggregates the gradient updates and also updates a set of parameters. Then we repeat this cycle when we ship out the next iteration of the model and train on the local data. And then we can continue to do this until the global model converges. So another privacy technique is differential privacy. So this method efforts individuals a privacy guaranteed that is statistically similar to the exclusion of their data. So in other words, when we are training machine learning models, we want them to basically learn from the general trends in the data and not conditioned on specific samples, because that could lead to the leakage of the training data. So how do we implement different privacy practices, differential privacy in practice? With the differential privacy, the goal is to give each individual roughly the same privacy. So that privacy would result from having their data removed. So that is, the prediction should not overly depend on the data of any of the individuals. So we apply some noises to weight updates so that the model parameters do not depend on too much on every single sample. So in this case, there are different types of noise. So we can add a noise to the data sample, we can add noise to the label, or we could add noise on clipping the gradient updates. So it's important to mention that the true confidentiality and privacy are difficult to achieve. So we need to remember that. So especially considering that we have to use different techniques and frameworks and models. So therefore, the need for CAPC, which is a confidential and private collaborative learning, which has a really appealing guarantees CAPC. So the CAPC building on private aggregation of teacher ensemble. So these methods have been developed by one of our faculty member, Nicola Peppernote at Vector. So PATE uses noisy functions on constituent model outputs to achieve differential privacy. So the CAPC uses PATE, and CAPC combines multiple PETs to provide highly flexible tool for collaborative learning. It combines specifically homomorphic encryption, secure multi-party competition, and private aggregation of teacher ensemble. So if you're interested, I highly recommend you to look at the CAPSI paper and learn more about the method behind this approach. So let's have a quick look at the Vector's PETS project. This project was designed to explore PETS and apply learned techniques and build proof of concepts based on participant use cases. So participants have been provided reference implementations, and they worked on different use cases using open source data. And participants formed over around like 20-25 teams, and they were from the public sponsors, including financial and banking institutions, consulting, manufacturing, insurance, healthcare, telecommunication, and public services. So as you can see on the left side, most of the participants explored federated learning and differential privacy. And some of them worked on CAPSI and homomorphic encryption. Here, so I would like to show some of the highlighted use cases that was explored over the project. So few teams explored vertical and horizontal federated learning using split neural network architectures. So we know that one advantage using federated learning is that the model can be trained for a joint prediction task without the need for a data to ever be removed from their silos. And then different entities providing different types of data. Those data could be structured, tabular, unstructured, free text. And the different types of data residing in the different silos could be combined in a single model. So use case were about insurance. And the problem was, will an existing insurance client buy an insurance policy or not? So this is a binary classification target variable. And then they partitioned the variables into two sets of features. So in-house variables accessible by the insurance company, and the third-party vendor variables whose raw values are inaccessible by the insurance company. So we had two groups. Those the participant built a vertical federated learning model using split neural network architecture, then compare the prediction performance of the baseline model versus split NN model. So split neural network architecture achieves the performance of the baseline model, which is great, but we have to test that achievement is trivial or not. So another interesting use case was combining Airbnb reviews and listings. So in this use case, the aim was to predict the review scores for each listing. And then the last example use case using the federated learning is a mimic data set. Mimic data set is in the health-related data set. And the group aim was to predict in-hospital mortality rate with a vertical federated learning using, again, split NN. And the use case has been created assuming that the different data sets are residing in different hospitals, for example. And they found that the split neural network model achieved the predictive performance of the baseline model as we've seen in the insurance case. And then split neural network technique works best with the simple fast-forward neural networks. And of course, more analysis needs to be conducted on different models across in different data sets. So another set of use cases explored the differential privacy, membership attack, and combination of differential privacy and members inference attack. And one use case specifically used differential privacy in predicting in-hospital mortality. And it was observed that the performance dropped with differential privacy and PATE. With a membership attack, the model performance dropped. So I think I don't have that much time to explain all of these use cases. So I would like to move on to some of the key observations and insights from the use cases. So in terms of differential privacy, most of the teams mentioned that the data preparation have a significant effect on the results. For example, a data normalization and working on class imbalance especially when using differential privacy, was essential. Another important observation is that a trade-off between privacy and accuracy. So we have seen that the differential privacy reduces prediction accuracy, but improves privacy. So I think it is very valuable to check for maybe the class levels, for example, underrepresentative classes when we dealing with the class imbalancing. So we also observed that the testing with the different noise addition have different effects. Another key observation is that the PATE shows better privacy than differential privacy, and better for release of model or unlimited access to the model output. And we also observed that the few participant teams have explored differential privacy with membership inference attack, and observed that the testing basic vulnerability to membership inference attack is not very complicated. And then some groups explored some techniques such as dropout or regularization and defense against the membership attack. And then they observed that the differential privacy performed better with inference attack over dropout and regularization. So regarding the federated learning, we have seen that the split neural network component introduces a risk for predictive performance. So it needs to be ensured that the split NN approaches, the predictive performance of the baseline model is non-trivial. So we also observed that the model of the server party, which could be a vendor, must be built from scratch. And then some observed that model agnostic approaches, for example, CAPC, is promising. And finally, we have observed that in a couple of use cases, horizontal federated learning has given a better performance result than vertical federated learning. So in terms of a general insights, although we have reviewed PETs in the production with our experts from AI engineering team where Devel is leading, the production requirements of these technologies still remain unclear, and especially the implementation details of engineering components in different infrastructure. So we need to plan of those engineering components well advanced. So last but not least, these technologies also needs to be planned not only the engineering components, but also the data pipeline, data structure for organizations, and governance of the model and system, and so on. But before I complete my talk, I'd like to acknowledge my team from the project management, AI engineering, and huge support from the project academic leaders and other members of Vector. And with that, I'd like to thank you so much for joining my talk. If you're interested in this project and learn about the reference implementation and the code, so we open source the models and implementations, and you can visit Vector's GitHub page. And if you'd like to more about what Vector is doing, so you can sign up our newsletter to learn more about our work. And please send us any questions or any comments to my email or Industry Innovations email. And I would like to wish you a great rest of the day.
Thank you, Sedef. It was a really mind-blowing presentation.